Hey guys. So in this video, I just want to sort of have a layman's kind of discussion about some physics stuff. In the background, I'm going to be having Universe Sandbox, just because I thought it'd be just nice to have something in the background, and this sort of applies to the topic. Now, before I get started, I'd like to mention, I am by no means a physicist. I took AP Physics 1 and 2, and I've sort of been interested in physics my whole life, and I've learned certain things. So all of this is just through that perspective. I'm not an authority on this topic, and so I just want to sort of have a discussion about how I've been thinking about gravity recently. So physics for the last few decades has sort of been trying to achieve quantum gravity, which is to say that it wants to create a quantum mechanical explanation for gravity. Now, what that entails is, from my understanding, in quantum mechanics, a force is modeled as an exchange of particles, essentially. So, if we, the camera here, are like an electron, and this Earth is another electron, if we were close enough, I haven't played this game in a while, then essentially what would happen is they would launch a photon at one another, which would transfer some energy. Obviously, this is a planet, so don't worry about it. But basically, there would be an exchange of particles between them. I'm pretty sure there is a thing in that game for this. And no, it's not watch. It's the other tool set. And essentially, that's how these fundamental forces work. It would be something like that. You know, like, it's just particles being exchanged. So in order for gravity to be such a force, you need to hypothesize what would be known as the graviton, which would be the particle that transfers gravity across distances. And obviously a lot of people have already pointed out the flaw with this idea. Roger Penrose, for example, Eric Weinstein and such. There's a lot of people who don't really think that this is the right approach. The alternative approach would be you maintain general relativity, where you have some classical space-time being curved, and so gravity is not actually a force in the same way as, say, electromagnetism, but it is simply the result of objects traveling the least distance through a curved space-time, essentially. And there are some physicists who are trying to pursue that sort of line of thinking. There's a man called Oppenheim, not to be confused with Oppenheimer, who has recently been a part of a stochastic sort of theory of gravity, which is a very interesting idea, and I recommend you look into it. But for this sort of talk, I just want to talk about gravitons in general, and why I think they don't make any sense. Because let's sort of, get into this. I think my first sort of idea was about Faraday cages. Now, again, I have no idea, how any of this stuff really works on a deeper level. But in like a layman's perspective, what a Faraday cage does is you take some wavelength of light, and if you have holes that are small enough, then it's as if the holes aren't there, because as far as that wavelength is concerned, this is a solid piece of material. And so a Faraday cage, for example, on the inside of your microwave, will prevent these microwaves from leaving, because the waves are so large and the holes are so small that it's as if there are no holes, and it simply is just absorbed into the cage itself. If we're viewing this as a force exchange, because if light is fundamentally the particle that transfers the electromagnetic force, then the light we see is a transfer of a force. It is a force. The sun is imparting a force onto us when we look at its light. But we can block light. There's a lot of ways that we can block light and redirect it and move it around. That much is clear. So the idea of a Faraday cage working with light makes tons of sense from a layman perspective. It's like, okay, well, you could put like a blackout curtain and that will block a lot of wavelengths of light. So the idea that you can have this piece of metal that does a similar thing, it kind of makes sense. And again, I'm oversimplifying things, but this is from a layman's perspective. So if here's a question, right? Is that due to electromagnetism, or is that due to the particle nature of this force? Like, from a quantum mechanical perspective, supposing you could have a Faraday cage of the right size, could you have a Faraday cage for the other forces, like the strong force or the weak force, for example? Hypothetically, if you could have a Faraday cage the size of like a few atoms or something, or smaller, obviously, then could you have a Faraday cage for that? And then the next question is, if gravity is one of these forces as well, could you have a Faraday cage for gravity? So in a sense, could you put something between a black hole and the Earth and prevent an exchange of gravitons, and thus preventing gravity between them? To me, that sort of seems ridiculous, but of course, I'm hypothesizing in the first place that you could do such a thing. But it sort of got me into the mindset of how I'm going to approach this. So, detecting particles, right? One of the hardest family of particles to detect are neutrinos. They are incredibly, like, tiny, and yet there are trillions of them running through you at this very moment. The thing is, they just don't interact with matter very much. And yet, even these things that basically never interact with anything, we detect a handful of these every day. And by we, I mean, you know, physicists at colliders, for example, or at different detectors. Those things that interact with nothing, almost, are constantly detected. And yet, we want to hypothesize that there is such a particle as a graviton. It's taking a long time to load. And it has to fundamentally interact with basically everything, and there would have to be trillions of them, because everything is undergoing gravity to some extent. So there would just be an absolute shower of these things. They would be everywhere, and yet we've never detected one. This would be on the scale of never detecting photons. Like, think about, like, what things in the universe have electromagnetic charge, right? It's a good amount of things, but not everything. But, like, how many things in the universe have mass? A lot of things have mass. Every single one of them would be emitting these gravitons and would be absorbing gravitons to be being attracted and to be, quote-unquote, warping space-time, if we're imagining in this scenario that general relativity is more of like a derived thing rather than the underlying nature. I hope this isn't stuck. I'd hate to have to restart this and then edit it together, but if everything's emitting these particles and everything's absorbing them, then how have we never detected one? And here's another question. If these particles are everywhere, like, in order for a particle to be absorbed, you can't be picky, right? You can't be picky about what absorbs it. How does a graviton from the sun, which would be holding, say, the Earth in orbit, how does that graviton ever reach past the surface of the Earth? Because these particles, they either interact with things or they don't. So the more mass that this particle has to go through, the entire atmosphere, buildings, miles of ground, how did these gravitons ever reach through the planet? Now, that might not be the best criticism, because you could try and make a similar criticism for photons if you didn't know that they existed. You could say, well, how do photons ever reach out of the center of the sun? And the answer for that case is, well, essentially, they just bounce between atoms all the time, and then they're re-emitted, absorbed, re-emitted, and then eventually they make their way out. You would have to hypothesize something similar for gravitons, or have some explanation for how do these gravitons make their way through the whole planet. But here, to me, is going to be the biggest criticism, although I'm going to fix this, so give me a moment. My biggest criticism of the graviton is actually black holes. So, again, we're hypothesizing that you have this particle, which is being emitted by everything, and this is what is responsible for gravity. We can view gravity as an exchange of gravitons, correct? That is, from my understanding of how forces are represented in quantum mechanics, that's how I view gravitons. So please correct me if I'm wrong in a nice way, because again, this is all just uneducated, sort of, in a sense. How? Oh, is my time frame way too quick? I think the Earth just got obliterated. Okay, that's a bit better. How, exactly? Here's the fundamental problem, I think, with the graviton that I'm not sure physics has really approached. Because we have a lot of these theories that will hypothesize a graviton. But the question that you must answer is, how do gravitons escape a black hole's event horizon? Because if these are just another particle, the same way as photons or neutrinos or anything else, then they should be bounded by a black hole's event horizon. And most gravitons, at least from my understanding, are either hypothesized to be the speed of light or lower. And therefore, what you would theorize, if you had a universe with gravitons, you could never have black holes with gravity. How do black holes have a gravitational force if every graviton that's emitted by it never leaves its event horizon? Because that's the thing about black holes. The event horizon isn't a physical sort of surface in the same way that like a tabletop is. It is a physical barrier, but it's more of a mathematical... It's like the event horizon, rather than being like a surface made up of matter, is simply the area in space beyond which light doesn't escape, which is why it looks black. So what that means is all of the matter inside of a black hole is within the event horizon. It's not on the surface of the event horizon, it's within it, it's deep within it. That is well accepted physics. Also, I like this gravitational lensing, that's really cool. But, so, that means if there is to be a force between the matter inside of a black hole and the matter outside, such as this orbit here, or suppose I take something like Jupiter and I just put it still, this is what general relativity would anticipate. You would have an attraction between them, which is exactly what we observe. But what that would imply is that there were gravitons being emitted from this black hole into Jupiter, and there were gravitons being emitted from Jupiter into the black hole, and then they collided. If this were the case, right, that gravitons could never leave the black hole, then if there were a force of gravity, it would have to be one way, and the mass of a black hole wouldn't affect its gravity, but that's nonsense. That's clearly nonsense. So, I'm not trying to say that gravitons definitely don't exist, but any theory of a graviton needs to explain this, because I think this is a massive problem, and I don't think most physicists who believe in a graviton have a good answer for it. How do gravitons exit a black hole? We could talk about something like Hawking radiation, but Hawking radiation isn't like... It's not a lot of mass that exits a black hole via Hawking radiation. It's like the occasional particle in a sense, right? The gravity of a black hole could not be represented by an occasional emission of gravitons. It simply can't. The larger the black hole is, the more gravity it has, and that would imply the more gravitons that need to escape. In order for a black hole to have the gravitational pull that we know that they have, then they would have to be emitting trillions of gravitons. But there is no mechanism by which they could be doing that. They simply cannot. So either we have black holes the way that we observe them, or gravitons exist and black holes just don't have nearly the gravitational pull that they do, or there is some mechanism by which this occurs, and if that mechanism cannot be described, then I don't think we have a good description of gravitons. It really just bothers me. I don't see a way around that. If you want to hypothesize this particle, then you need some explanation for this. Not only that, but general relativity would also state, because again, right, this is the whole idea of quantum gravity is to reconcile general relativity and quantum mechanics by making general relativity explained through quantum mechanical phenomena. But what that would imply is every prediction of general relativity that is accurate, not necessarily all of them, such as a singularity, some of those things might just be the consequence of the model being inaccurate, but certain things like gravitational waves, those are things we've observed. General relativity would say a gravitational wave could pass through a black hole. Now, why is that? Because it's not a wave that's inside of space-time, like drawn on paper. It's a wave in space-time, or like of space-time. So instead of like trying to draw a wave on a piece of paper, it's more like wiggling the piece of paper. But again, if this force, if these waves are represented by gravitons, these gravitons wouldn't be able to be within space-time in the same way that every other particle is. Maybe that's just my misunderstanding there, is if space-time, if you're viewing, okay, if we're viewing these particles and waves, it's always talking about a field, right? You have these waves through these fields, and then they manifest as particles in points in that field. So what that would imply about a graviton, should it exist, it could not be like the other fields. The field of the gravitational field would have to be the classical sort of space-time. And what that would mean is the graviton would be in space-time. It wouldn't be inside of space-time. It would be sort of space-time, I suppose. That's what it would have to be like. So it would fundamentally still be a different force, even if it were a force. So maybe this whole video is completely useless because that's the answer. That if a graviton exists, it's not a particle inside of this in the way that, say... I already had it. It was up here. In the way that these are particles in space. Right? These are particles being launched through space. It wouldn't be like that. It would be like particles of space, in a sense. But doesn't that feel a little like... I don't know, it doesn't feel sort of like as unified as they like to claim it is, but again, I'm not a physicist. Maybe this is exactly what physicists mean when they talk about gravitons. But I think if that's the case, then they need to be more precise in their speech about that. But certainly, if a graviton exists in space the same way that photons do, then this is a massive problem, because they should not be able to leave a black hole. So you'd have to hypothesize somehow that these particles are of space-time, in a sense. I'm not sure. Let me know your thoughts in the comments. Let me know if I'm just completely off basis and just need to read more books. But, I don't know. I think this is interesting. I've never thought about this until this morning. So I thought, you know, just make a video. See what other people think, because I did look up this sort of thing, and people haven't really talked about it, so... I'd hate to believe that something this simple just hasn't been considered by other, like, physicists who do this for a living. I'm sure people have thought about things like this. Oh, look at that gravitational lensing, that's amazing. But yeah, I don't know. So, yeah. Let me know what you think in the comments. Hopefully this made you think more about things at least. And if you like videos like these, then let me know and maybe I'll make more of them. See ya.